just as a bit of background, and this presentation isn't overly technical. By the way, how's that for the volume? Is that okay? Good? Yep, okay. It's not overly technical, but there's kind of lots of ideas here and things that we've done that I want to pass on to you, and hopefully there's a few things to get you thinking about buildings and the engineer's role in buildings and how we can make buildings better places. So the impetus for this whole project came about a couple of years ago. As John mentioned, we've been growing fairly rapidly over the last few years. Yeah, he didn't tell you about the 20 years where the phone didn't ring. Consultant available for hire, could just call this 1-800 number. So, as we say, 25 years to be an overnight success. So, we've grown rapidly. We essentially outgrew our office that we were in Kitchener, and we needed a larger office space. So. And this is it. So there's some promotional stuff here. We've been growing, as I said, very rapidly. But this is the building that John referred to. This it's called Green on the Grand. It's on Riverbend Drive. It was part of a competition that the federal government had back in 1995 to build green buildings, and there wasn't a lot at that time. In fact, if any, and we responded to that competition. The deal was we went to a local developer and said, we'll rent the space if you build the building and make it according to our specifications. And this is the building that went up. And we, of course, monitored the energy performance of the building. And this is a metric I'm going to use throughout today, is this kilowatt hours per square meter. So it's the amount of energy consumed, both natural gas and electricity. So we take the natural gas, convert it into an equivalent energy in kilowatt hours, divide it by the floor area of the building. And so it came in at 130. A typical building runs about 400. And we'll talk about more later, at least a typical Canadian building. So at 130, we made the claim that we were the most energy efficient building in Canada, and I went around giving talks like this, waiting for someone in the audience to jump up and say, well, no, we've got one that's 100, you're a liar, and no one ever did. So I stuck with that. Although actually I am pleased to say there is now another building that's past that, John and I were just talking about, the Manitoba Hydro building, I think is running around about 90 is where I'm hearing it. But no, I heard it was measured, but I haven't seen it published. At least it's not published. Peer-reviewed published. It's not out there yet. But at the time there was nothing close to this. So we were pretty happy with that. But again, it was too small. We had to move on. So we needed a new building. So we set some goals for our new building, and this one would be, instead of just being a tenant in the building, we were going to be the prime tenant, or the only tenant in the building. So a couple of things we said. First one is we wanted it to be at least in Canada, the first triple LEED Platinum. And for those that aren't familiar, LEED is a green building rating system. Some terminology here, NC means new construction, CI is commercial interiors, which is essentially the fit up and the furniture that you put in. And then EBOM stands for existing buildings operation and maintenance. So it's how do you build the basic building, how do you fit up the building, and then how do you operate it over time. And actually we just heard there actually is another triple LEED Platinum building in Michigan. So we don't get a North American first. We'll have to settle for a Canadian first. So that was number one. So, and Platinum is the highest rating that you can get, and of all the projects that get LEED certification, only about 5 or 6% actually get the Platinum level. The vast majority obviously are less than that. We also wanted to then, we took Green on the Grand, and in fact, when we go back there now, we kind of walk around and some of the technology looks a little clunky. We were using T8 lamps, which were, the height of new technology at the time. We've got these great big light fixtures, indirect lighting, that you look at them and they're not nearly as slick or slim as the units today, and so on. And we said, we should be able to do a lot better. We're 10 or 12 years smarter. There's a lot of new technologies. And pretty much just on a whim said we should be able to cut that 130 in half and get it down to 65. So set that as a target. If you don't have a goal, you won't get there. So, but the other thing is it also relates to cost, because my view is anyone can make an energy efficient building if you have an infinite budget. Just take your building, cover it with wind turbines and photovoltaic panels and everything, and just generate all the power, and away you go. So you might prove it from a technical point of view, but unless it's cost effective and that the marketplace can then embrace it and roll it out, it's really not going to go anywhere. So we wanted to show that it could be done in a cost effective manner. Fourth bullet there is to provide a quality workspace. When you go and hear these lectures about green buildings, one of the benefits is to the employees, creating a more productive workspace for employees. And there's all sorts of various studies and guides that talk about you pay, it's a factor of 100 difference between what you pay per square foot for energy versus what you pay per square foot for the employees sitting in the building. So one of the tenets of green buildings is you never sacrifice thermal comfort or quality in order to get the energy saving. So that's sort of when we go back to some of the early sort of 1970s and 80s building, they were getting great energy performance by basically shutting off ventilation air, giving people little minor lamps for working on their projects and so on. So green building says, no, you don't do that. You want a quality workspace. So I drank the Kool-Aid and said, yep, okay, that's what we want to do to create an attractive, productive, and healthy workplace. And then lastly is revitalize the neighborhood. So you'll see that in a second. So it's also about there's a community aspect here as well. Acknowledging our team on it, the architect, Robertson Simmons Architect, which is a local firm in Kitchener. We provided a number of services. We did the mechanical, electrical engineering on it. MTE, again, a local firm, were the civil and structural engineers. We were the lead consultant. We also did the commissioning and energy performance monitoring, and I'm going to show you some of those results. Elemental Design, Interiors, and Landscape Roth Associates. Oh, and Malo Blamey were the contractors. So this is essentially the final product. So it's called a grander view. So there's a little bit. The earlier one was called Green on the Grand, and Grand referring to the Grand River. So we were right on the Grand River. So we had this one, and we're actually 2 building lots upstream of our old building, also on the Grand River. So we had to come up with a clever name. So there's a double entendre here. So it's a grander view. So it's still on the Grand River, but a grander view of our last building, if you like. So it's about 2150, so about 23,000 square feet of office space. As you can see, there are 3 stories, designed for 90 employees, and that's the Grand River right there in the foreground. So the original site, and only in Kitchener-Waterloo would we do this. This is a prime waterfront property that is actually used as the sewer outflow for the city of Waterloo. That little shed you see in the middle is actually a water sampling station, and if you look down on the far right, you can see Waterloo's sewage going out into the Grand River. So chunk of land that really was, who'd want to build by the river when you can build right beside the train tracks and have real good train access. So this, if you can believe it, this land has sat vacant for all the time that us folks have been here. So it was used for parking trailers and things like that. And so we said part of a green building is also about, again, revitalizing neighborhoods. It's about urban densification and creating more livable cities. And so we, again, wanted to be all part of that. So here's the site. So the Grand River is on the far right side, the building at the bottom, and like a true architect, north is straight up. So you can see the building it actually runs due east-west. So the major facades are both north and south. In terms of the landscaping, there is no sod on the property, so no grass. It's all native plantings. We have employee garden plots, recycling containers. That central island is a stormwater detention pond. And then again, part of that community aspect, we donated some of our land to the Grand River Trail. So before we were in there, the trail came to an end. We've put it through there, and now people can walk, connect there, not the least of which of our employees can go for a lunchtime walk as well. So just some shots. Now, of course, these are early. The landscape hasn't fully come in, but this is that central area that we use for a stormwater detention pond. You can see that we take the water, I bet that's what this thing is. So water goes off again, typical approach is you take the stormwater off the parking lot, you collect it in a catch basin, and then we just dump it into the Grand River, out of sight, out of mind. So what we do here is instead of that, we seem to have lost. The water drains off here, goes through here. This is a bit of a swale that goes down. So we're using the landscaping to sort of treat the water, get some of the solids out, goes through a storm scepter, and then out to the storm water system. So we try to clean the water before we leave the site. These are the employee garden plots that we've put in so we can grow our own food locally. This is the video I never got to work, so this would show you some construction shots that I'll just show you the real building instead. So on the inside, just so what it looks like, the focal point, if you like, the lobby of it is an atrium. It's a 3-story space. We had this piece of artwork commissioned, and again, that's part of green buildings, that attractive part. This is an artist in California, and it's the artist's representation of the Grand River, and this is supposed to represent the spring melt. And you can see it's kind of blue and white for the ice, and you go through here, it turns blue, and then by the time you get down to the fall, it's starting to fill up with algae and looking a little greenish or whatever. But so we put that in there. Interestingly, and here's research projects we're talking about. So this is a skylight we put in there to provide natural lighting in there. And initially, the concept called for vertical glazing was sort of a top hat. So you put in glazings north and south and a little roof over it, an overhang, and you shade it. And one of the things we did with our design is we sent it out for a peer review, which I'm a big fan of. If you want really good buildings, give it out to other experts, have them look at, have them critique it. And we had a fellow in the States critique it, and he looked at it and he said, I know exactly why you've done that. That's what all the textbooks say to do, because you don't want that large solar gain to come through and cause a cooling load and so on. He said, take a look at it. He says, I think you'll actually find a sloped glazing will perform better. So what the issue is, so this is actually facing due south. This is a solar control glazing. So this is the, John will know this, Solar Band 70. So it has a glazing that has high daylight transmission, but it cuts out most of the solar heat gain. But the issue is, had we put it vertical and put an overhang on it, because that's not the optimum angle, we would have gotten a lot less natural light in there. And since the purpose of it is to put in natural light, if we wanted the same amount of natural light, we would have had to make it bigger and bigger. And we're adding more and more window area to get the same amount of light. And so with the solar control, we dealt with the solar gain thing, and we've put it in for the optimum orientation to get the daylighting in there. And so when we ran our energy models, in fact, our peer reviewer was in fact correct that this actually worked. It was a more energy efficient option, which frankly surprised us, and I think it surprises a lot of people because it's not what the normal daylighting textbooks say. And from a practical point of view, we haven't run into problems in terms of it being hot up at on the 3rd floor and cool in the bottom. It seems to work fairly well. Typical office spaces, lots of natural light. I'll talk about this in a second. It's a very narrow building. These are our meeting rooms over here. So all our rooms have windows, even meeting rooms. Glad this one does. No one is any more than 15 feet from a window. So all of the workers in there are at least within 15 feet of a window, and that includes meeting rooms. Again, typical office layout, fairly generous workstations. These are casement windows, so operable windows, so that if it's a beautiful day, you can open the window. Again, mechanical engineers aren't supposed to like operable windows. It upsets the mechanical system, but whenever you're voting, people get the first vote. So they say most people would like operable windows. If it's a nice day outside, they want to be able to open the window, and heck, why not? So I mentioned this. So our building is only 12 meters wide, 40 feet wide, and it's 200 feet long. So it's a really long and skinny shape. Again, conventional thinking or philosophy is, we should have it as a square or a cube because that has the minimum surface area. And of course, we're always worried about heat loss. Keep that minimum surface area. But what that does, it means that you have an awful lot of interior space. And if you have an interior space, obviously it's not getting lighting. And I think the other aspect, and again, it ties into the mechanical system, if I have a building with an interior space, it is going to require cooling 365 days of the year. Even on the coldest day of the year, because it's an interior space, it has no heat loss, it needs cooling, whereas the perimeter space still needs heating. And frankly, most of mechanical engineers spend their career trying to figure out how can I deal with those two issues of some of my building needing heating, some of my building needing cooling. And so they have to devise fairly complicated mechanical systems to meet those two needs. And invariably, they end up being extremely energy inefficient because you're doing both heating and cooling at the same time. By having a very narrow building where everyone is in contact with the perimeter, the building is either all in heating or all in cooling, and it greatly simplified our mechanical system that I'll talk about in a second. So we had done that primarily from a daylighting point of view so that everyone could have that natural light in their space. So the actual construction of the building is, I call it, it's like Lego. I sometimes say glorified Lego, but maybe it's not even glorified, it's just Lego. It probably shows in the next slide. Yeah. So what it is, the walls are made out of ICF, so it's insulated concrete forms. So these are the Lego blocks put here, and you just stack them up on top of one another. And then the concrete trucks comes in and they just pour concrete down in between. And you keep the foam there. So if any of you have driven along King Street lately and seen all those new apartment buildings going up, the student housing ones, they're all constructed this same way. It's a very inexpensive way of building buildings. But not only that, it's a really well insulated system because you can see here, there's no thermal bridging through there. You end up with a solid layer of insulation through there. So we think it's actually a winning technology. So we build up these Lego blocks all the way around of that, and then we put hollow core precast slabs that are 40 feet long. We just plonk those on top so that in fact there's no interior columns in our building. So all the interior designers love that because typically interior designers spend all their lives trying to work around columns. Okay, I see you've got a little cantilever here or something going on. So whenever you have a column, it's always going to cut into the functionality of the space, and if you're doing it properly, it means you got to make your building bigger to account for the unusable space associated with columns. So it ends up being a very simple construction. I skipped a slide, I don't know. So that's just another view of it. What I did want to point out here is, so if this is your office, you can see we have windows. This is the north side, that is the east side, and then down probably the other side is the west side. So on all these office spaces, you've got light coming from two sources. You can kind of see here, there's no shadows going on here. So again, part of daylighting design says make sure you get light from two sides so you don't get glare or a lot of contrast. So with that envelope there, it comes out to about an R25 wall. We've got roughly a 40% window to wall ratio. You can see it down here. We sort of pushed this technology as far as you could in terms of we wanted fairly large openings to get good daylighting in there, but we wanted to make sure it was effective. So we do have a sill that goes there. It's about a 2-foot sill there, and you can see the operable windows here. This is during construction, but you can see that they're open there. Windows are triple glazed, low E argon, warm edge spacer and fiberglass frames. They're essentially the most efficient you can get. By going with those windows, we eliminated perimeter heating, which I'm looking at, looks like you've got it over there. It's kind of it's sort of classic how not to design a building, no offense to anyone around here. You put in really lousy windows that lose a lot of heat, and then you say, how do we make up for it? Oh, let's put a whole bunch of heaters along there to make up for the lousy windows. So our kind of thing was, well, why don't you put in better windows and get rid of that perimeter heating? So, and what ends up happening is, yes, the windows cost more, but you save more on the mechanical side, so you end up ahead of the game from a cost point of view. Some of the other technologies we put in there, and we were talking about this earlier. So we have automated blinds on the outside. So here you've got blinds, but they're on the inside. The problem with the blinds on the inside is typically you put them down to deal with solar gain or solar control. So you put them down, but the blinds will absorb the solar radiation. So they deal with glare, but they don't deal with getting rid of the solar heat, because the solar heat's already gone through the window, it's in the space, your air conditioner is going to have to get rid of that. If you put it on the outside, it then deals with the glare, and anything that's absorbed there will get lost to the outside, so it doesn't increase your cooling load. So these are all automated, so it's done on solar radiation and wind. So if there's direct solar radiation on these, which would cause a glare problem and undoubtedly a solar heat gain problem, those blinds will come down. We've got a 6 kilowatt photovoltaic system on the roof to generate some power for the building. On the water side, we use a rainwater cistern. So we have a 30 cubic meter rainwater cistern. So we collect the rainwater off the roof. It goes into the cistern, and from the cistern, it provides almost all of the water for our toilets, urinals, and there's even a hose bib outside for the employee garden. Again, this is a typical washroom, so we've used the most efficient fixtures you've got. We wanted to get the water heating load down on the building. So again, all Energy Star fixtures throughout. And then another one that was kind of, it seems like a no-brainer, it's just never done. When we look at the office of today, you get to sit in the front row. It's when you come 20 minutes in. Oh, you brought me a sandwich, thank you. Better than an apple, right? Yeah. So the office of today is pretty much, it's all server-based. It used to be there was a computer on every desk, and of course there was a lot of heat gain associated with that, and you'd have to figure that into your mechanical system. Now pretty much what happens, it's laptops on desks, much less power, but all you've done is move the power down to your server room. So we, like pretty much every other office now, we have a large server room in our office. Server rooms require cooling, again, 365 days of the year, just a lot of heat given off by these server spaces. The vast majority of buildings then just are dumping that heat outside. They will run air conditioners all year long to get rid of that heat. So what we said is, well, that's kind of a waste to get rid of all that good heat. So we have put a heat pump in there. The heat pump cools the server room and then provides hot water for our showers and our faucets and so on. So it's pretty much of a no-brainer. It doesn't do much. And then what we do is we have small electric tanks locally that just provide that top-up in there, and we don't have a recirculation loop. It's also shut down in unoccupied hours. That'd be the electric tanks. The ventilation system, we use a technology called earth tubes. It comes out of Europe. It's used over there, I'll say a fair bit, fairly new to North America. It's, again, pretty basic, and you can see the construction going in here. So this is concrete sewer pipe, and then this goes up here, and eventually the soil will all fill in here. So fresh air for our building comes in, goes down across and into the building, and what we're using is the thermal mass of the ground to either preheat the air in the winter or pre-cool the air in the summer. So the earth is a great big thermal flywheel. So, I mean, that's why all our water supply, we bury them 3 or 4 feet underground, because the ground there it doesn't freeze. It's pretty much constant temperature year round. So we're taking advantage of that, using this to temper out the air and reduce both the heating and cooling load on our supply air. From there, the air goes into ERVs, which are energy recovery ventilators. They're just heat exchangers that I take the exhaust air from the building that's going out from the washrooms. I'm using that air to preheat the fresh air coming in. I don't transfer the air, I just transfer both the heat and the humidity. And then that's it. We just blow the fresh air in. It pretty much doesn't need much heating and cooling after that point. The actual heating and cooling system, we're using a technology called variable refrigerant flow, or VRF, widely used in Japan. And what it is, these are essentially the heat pump units. There's 3 of these on the roof, and then there's a series of essentially fan coils connected throughout the building. So I think we have something like 60 of these little fan coils. They're all strung together with refrigerant piping. So the refrigerant piping is that very small, it's like 3/8 of an inch diameter piping that connects all these, and refrigerant runs through it. So there's no water piping in our building for heating and cooling, it's just this refrigerant. So if it's a cold day, these things run, they will pull heat out of the air, produce heat, and that's how we heat it. flips over in the summer and reverses. Each one can either be, one can be in heating and the other two can be in cooling or whatever, it does that. But one of the beauties is we have all of these individual fan coils. So if you remember back, I said we designed it for a staff of 90 and we have 60 of these things. So we've got essentially one thermostat for every 1.5 people in our space. Typically, I dare say in this room, we have one thermostat for, whatever we got, 50 or 60 people. And that's pretty typical. And trying to get the cost of mechanical systems down, you try to make zones larger and larger and rely on one thermostat to heat a whole area. And engineers are funny. We have this, there's a standard, it's called ASHRAE 55, which is the thermal comfort standard. And you're supposed to use it when you're designing buildings to make buildings thermally comfortable. And the benchmark they've set is 80% satisfaction. They know we do a really lousy job of designing mechanical systems. So if we can get 80% of the people happy, i.e. 20% of the people are unhappy, we consider that's a good job. Okay? You can imagine if Toyota or GM selling their cars said, well, 80% of the people are happy with their cars, 20% hated their cars, they'd be out of business. But somehow we've grown to accept this frankly mediocre standard for thermal comfort. And the primary problem is, again, we're trying to get this system to serve one zone to keep 20 people happy. And the problem you have is everyone is unique. Whatever setting I put that thermostat to, and I ask people to vote, are you too hot or too cold? I'll have some people say too hot, some people say too cold. You need individual control to meet the requirements of people. And so that's what this does. Okay, we talked about these. That's just what these individual units look like, and they each have a thermostat connected to them. One of the other interesting things we've done here is, we're probably all familiar with occupancy sensors. Great technology. If you come into the room, the occupancy sensor sees you're there. Oops, I guess if you're here, you want the lights on. It turns them on. When you go, you're no longer there. It turns the lights off. Great control mechanism for lights. And what we said is, well, here's a technology, pretty robust, pretty reliable, pretty cheap. They're only about $30 or $40 a sensor. Why are we only controlling lights? So what we have done is all our fans are controlled by this occupancy sensor as well. So if everyone goes home, or if everyone goes home in a zone, and all the occupancy sensors say no one is here, we shut off the ventilation system. We also have it go into setback mode. No one's here, don't need to do it. Typically, how it's done in buildings, you probably have this in your own houses, we put in thermostats, we put in time clocks, right? Okay, people might show up at 6 o'clock in the morning, so I better turn the fans on at 6. They may not show up till 8 or 9, but because I don't know, I have to set up at 6. I better run the system to 10 o'clock at night or 12 o'clock because I don't know how long people are going to be here. And so you end up adding a few hours of operation, both at the beginning and at the end, in anticipation that people might be there. Again, controlling out on occupancy sensors, you've got perfect control. If they're there, it comes on, if not, going. So again, I think that was a huge energy saver in our case. This is sort of what the mechanical system looks like. So we have overhead supply. So this is the air that is coming in. We use these nozzle jets. They're like the nozzle jets on airplanes. So what we're trying to do, again, I never run into a problem whenever I give these lectures. There's always how not to do things. And so this, again, pretty typical practice. So this is a combination light fixture and mechanical diffuser. And this little gap here is where they bring air in. And they're usually designed so that the air comes in and they direct it sideways because they don't want to shoot the air straight down because they will often have to bring in the air very cold and could cause a draft. And then we put some return grills up here. And this is particularly brilliant. So here's where the fresh air is coming in, folks, and here's where the fresh air is going out. So how much do you think is getting to poor John here, okay? So I must take a picture of that. That's one of the best I've seen. So usually we put them at least 2 or 3 feet apart, but they didn't worry about that. So again, we like this idea of the nozzle jet. So here's my fresh air. The people are down, closer to floor level. Let's shoot that fresh air down to them. Again, I talk about it, everything controlled on occupancy sensors, operable windows. Oh, we also have daylighting sensors integral right into the light fixture. So it's real simple for the installers. They just wire them up it already comes with the daylight sensor. Couple other aspects in terms of green buildings. It's not just energy and water, it's also the materials you use to construct the building. So we had a little bit of fun with this. This is a church in Woodstock that was torn down. Actually, you can see it's in the middle of being torn down. We heard about this, got that beautiful stone, and we've used it as the exterior cladding of the building. And why not? It's great stuff. This is the St. Clair Port Huron train tunnel. That was, you can see it's decommissioned. I can see the weeds growing up. Heard about it, got this armor stone and put it, and we've used it as a retaining wall in our building. So we have a couple of other salvage materials we're using. So again, we're trying to make this building out of previous building materials rather than using virgin materials. All our paint is 100% recycled paint. And this is a relatively new technology. It's started in Quebec. We're starting to see it in Ontario now. You'll see it in some of the Home Depots and so on. They'll say, drop your paint cans off here. And if you go to the Waterloo landfill site, same thing, bring us your empty paint cans. So for a while, it was just so the region was doing it. So instead of you pouring it down the drain, they would take it there and they would dispose of it properly. Now what they're doing, there's a company in Quebec that takes all those old paint cans, they mix them together, and they have some magical process that actually removes the color from it. And they then sell this paint that's 100% recycled paint, and we use that. So don't ask me how they get the color out, but it's pretty neat, and you get a wide range of colors that you can use. So we use that. FSC wood, so that's Forest Stewardship Council wood, so sustainably grown and harvested wood, high recycled content for all our materials. This is the kitchen area. So the countertops are actually made out of paper. It's a compressed paper, and there's a resin in there so that it can get wet without the paper going soggy. Bamboo cabinets on here, and the Energy Star appliances throughout. Construction waste, almost all of our construction waste was then recycled, reused for something else. We have a composting program in our office, so all our kitchen waste and so on is taken, put out in a compost bin to be done with. And we have a neat photocopier that is a no-waste printer, that there's no cartridges with it. It's just like a resin stick you put in. Just use that for your ink. So in terms of performance, this is a note, operative word here, predicted performance. This is what, when we completed the design, did our energy model, how did we think it was going to perform? So we were looking at 80% energy savings. So a conventional building would have used roughly $60,000 in annual energy costs. We were hoping to come in under $20,000, and you can see that's the various end uses that we've cut down. Same thing, 80% water savings over a conventional building, and we were targeting 61 lead points. It's out of 70 is the maximum you can get. There's one other building in Canada that got, I think, 62 or 63, so it would be the second highest number of points on a building if we achieve those. These are, again, just some more of the numbers. A couple of key ones here. 99% of the offices have what do they call view to the outdoors. I'm not sure what the 1% is. And 98% had daylight to their office. So this is the real fun graph. This is where the rubber hits the road. This is the monitored energy use of the building. So building was designed, constructed. We moved in the end of September of 2009. So we've been in for about 16 months. This is that same metric I talked about earlier. Actually, it isn't. This is kilowatt hours per day, but same thing, equivalent energy. The green line is what our computer simulation says. This is what the model says, and you have to understand about the model. The model assumes perfection. It assumes all the occupants behave perfectly. It assumes all our insulation was put in perfectly. There's no gaps in it. All our mechanical systems are operating perfectly, and so on. And so we know from experience that that green line really represents the optimum. If everything's working perfectly, that's where you should get. What we find is, well, you're probably going to be typically 15 or 20% higher of that because of all the sort of things that happen in real life. And that's what this red line is. And so you can see up here, that's what we were calling expected performance. Based on our experience with other buildings, we thought it would follow the red line. The blue line is, well, that's where we think this represents that represents a high, this represents a low. So we would expect to fall between the green and the blue lines. Okay, so that's what we produced before we had any monitored results. So the black line here with the dashes is the actual energy use on a month-by-month basis. And you can see first few months, well, look at that, bang, we're pretty much tracking the red line, which is where we thought it was going to be. Interestingly, it starts sneaking up a little bit, but then we start tracking down. We're getting the red line. We're actually now going below. We're actually slightly below the green line and actually following it extremely well, tracking it very well. So there's a whole bunch of things going on here. First off, and this is very typical, when you move into a building, even our building, which was probably engineered to death, the stuff you put in never works perfectly day one. You've got to go and commission the building. And that's one of the tenets of LEED is about commissioning. You have to, if you put the stuff in, it isn't going to work perfectly day one. Any kind of sensors you put in are going to be installed with the factory settings. You have to go in and adjust them to match your what your needs are and so on. So throughout this period, this first 4 or 5 months here, we were going through that commissioning process, getting things to work properly. And that's where you're seeing here from going from the blue, we were actually improving over time as we were getting that system to work better. Secondly, if you sort of corrected for that, you can actually see a pretty good match between our predicted number and the actual number, which at least gave us a lot of confidence in if you can get the inputs right into your software, it's a pretty good predictor of your energy use. So we ended up, once we got it, working perfectly, it was actually pretty much matching what we said. The interesting thing, we've now been in the office for more than a year, so we can compare the difference. So this first dot here, this is November of 2009. That dot is November 2010. So same month, 1 year apart. And we've actually got a 25% reduction in energy use year over year. And frankly, that's all from both what we call measurement and verification, the fact that we were tracking this all the way along, and when we were following the blue line, we knew something was wrong. Wasn't sure what it was, but we knew something wasn't working in the building. We better go figure out what it is, and then correcting the problem. And so this is almost becoming a universal constant. We're finding that you can walk pretty much into any building and you can get 20 to 25% energy savings just by making sure everything's working properly.
Did you spend any money to get that 25%?
No, there's no new equipment. It's just all the same equipment. It's just working properly. So as one example, we found out one of our fan systems was running 24 hours a day. Wasn't supposed to be. It was supposed to be running on the occupancy sensor, but whatever the issue was, the wire connectors or the sensor, it was running 24 hours a day, okay? So we had to go and correct that. So it was a bunch of those little things. The only cost was essentially the person's time to go and find this. But yeah, so.
For everyone here, I did a similar thing for the food plant in India, and just did measurement and verification every day. They reduced their energy bill by $1.5 million, not investing one penny. And that was 15%. And that was a daily monitoring of the whole plant.
Yeah.
Just an email to every manager every day. 15%, $1.5 million.
Yeah. Sorry, question at the back? Yeah.
Is there a bit of a, I don't know if you publish this daily within the staff, but maybe there's a bit of competition. Okay, let's lower what we need to, okay, I can put up with 20, 19 degrees. And then, so that's why over the culture of the corporation changes to achieve these better numbers?
I'm going to say yes and no. So there was no, this isn't kind of a freeze in the dark, who can sweat it out the most or whatever. So I wouldn't say there's any of that. Having said that, we do have a kiosk in our lobby, and we have real-time monitoring of the energy use of the building. And we're starting to use this more and more, and we see this as the big thing. I think your point's well taken. Give the occupant feedback. And one of my ideas that I'm going to patent if someone doesn't beat me here, on that kiosk have a little green, yellow, and red light on top, and that people walk in, and green, hey, our energy use is good. Yellow, we're in trouble. And red, guys, we're using a lot of energy, smarten up sort of thing. And certainly we've seen a lot of this. Whenever you give, people want to be engaged. If you give that feedback, they can do that. So. Yep.
Do you think that you'd be able to get it down to the individual level, that sort of feedback the occupants, so you say this occupant's doing really well, maybe this one perhaps is.
I mean, there are systems, and you can do it. I mean, you run it through your network where you can actually put it to people's computers there. I mean, a lot of the energy use isn't down at the computer level. Now there is a system, DALI is the trade name, DALI, where you can put lighting control at the individual occupant level. I mean, the problem with most office buildings like this, overhead lighting, you walk in, it is what it is. And if you don't like it, tough, right? There's nothing you can do about it except for getting paper and taping it over or whatever. In the DALI system, it's an addressable system. So you can at your desk say, actually, you know what, it's a little too bright at my desk, and you can throttle it down, or conversely, you can move it up and down. And so some of the numbers I've seen is you get kind of 10% savings just off the top. That, again, you give people control and you actually get the savings. When you try to have this homogeneous, everybody gets the same, you don't get it. So pretty good news. So this is, again, just sort of saying the same thing, but this is broken out. This is our proposed where we thought it was going to be. You can see we ended up at that, a little over 65 here, but we picked up some PV down there. We were initially running at about 80 kilowatt hours, and we've now got it down, so we're actually running now slightly below our predicted value. So that target we set of cutting the energy use in half, we've now achieved. So how does that compare to other buildings? It's really important to put it in context. So this is a graph. I've presented this a few times. We have a lot of fun with this. So this orange bar is the average energy use of office buildings in Canada. And you can see it's just a tad under 400 kilowatt hours per square meter. And this is from Natural Resources Canada. They published this data. These blue bars, A through H, are a number of LEED buildings, green buildings that we've worked on, not our building, other people's buildings. And as part of that work, we go and do measurement and verification on those buildings. And you can see that the range that we're getting here, here's one at 150, there's another one here up in 350. Bit of a range. The average is sitting here, which is a 40% reduction. So big picture, 40% reduction in energy use is pretty darn good. It does show that we can make significant reductions. We had on our building, we're way down here sitting in at 68. So again, good news is we design buildings so poorly and so wastefully, there's huge potential for energy savings. This is the same thing on water. Data, frankly, isn't as good as what water consumption is. The best we could find is a typical office building. You use 50 liters of water per day per person. If you think of it, a typical toilet is somewhere around 6 liters per flush. Those are the new ones. Older ones are 13, maybe even 20 liters per flush. So, flush a toilet 2 or 3 times a day, use the lab faucets a few times, and you can see pretty quickly you're up at 50 liters per person per day. So what were we predict? We were predicting a total of about 14 liters per day, but 5 of that coming from the cistern, so we were only purchasing 8 from the 8.7 from the city. Our actual monitored number is our total demand is down a little bit. We're sitting at 7.9 liters per day, so purchased water. So again, huge savings. That's just a breakdown of where the water is used in there. Maybe I'll skip that. So again, I recently wrote an article that had the title the building was a success, but the patient died. In other words, we have all these architectural masterpieces that get put on the front pages of architectural journals, but never anybody goes back and says, well, did the people inside actually like the building? And so again, this is part of that, creating a building that people like. So there is, it's actually the University of California at Berkeley has developed a occupant survey. And they have had this survey used on hundreds of buildings across North America, and so they have this huge database. And so we went to them, we used their same survey, it's a web-based thing, so we had our employees fill out the occupant survey, the data all goes back to the university and they do the analysis, they give us a report back on how we did. So it asks a number of questions, it's fluffy if you like, it's how how happy are you with the lighting, the acoustics, and it's the standard, you know, very satisfied, satisfied, somewhat, hate it, and so on. So these were the numbers that we got back, and you can see general building satisfaction 100%, lighting 96%, cleanliness, air quality, all the way down. In fact, the only one that was really poor at all was acoustics, and I'll talk about that in a second, down at 49%. To me, more interestingly, it then puts you on a percentile. Of all these other hundreds of buildings that they've done across North America, where do you rank relative to those, okay? Well, I guess if we're 100, by definition, I guess you're in the 100th percentile, but look at this. So even though we're 96 in lighting, 99th percentile, 95, 99, 99, 96, how would you like these as your freshman average when you're going out for co-op interviews, okay? So even the acoustics is the only one that's down. We're at 70%. So even though only 49% of the people were satisfied, guess what? There's a lot of other buildings people aren't satisfied with. So again, I think it just speaks to the concept we had, and I think, frankly, this should become mandatory on all buildings. And you know, did the people like the building? And if they don't, then you didn't do a very good job. I don't care how many little architectural awards you have in the lobby. So, so having said that, we did recognize that, okay, it fell down a little bit on the acoustical quality, and what's that issue? The design of our system is there's essentially no white noise in our office. And if we're all quiet, you can hear the white noise here, that little hiss. You can debate whether it's purposely designed into the system or not, but it's a sound masking technique. And we do have a fairly open office concept, so we do get a fair bit of noise transfer from one workstation to a next and so on. And I think that's where the comment was coming from. So we did a couple of things. One was that we actually did put in a sound masking system in some of those critical areas where that was important. So this is just a summary of where we are. So actually first year monitored results, energy savings, again, post-commissioning we're at 83%. Remember our target was 80, water savings target 80, we're sitting at 84%. So usually when I give this presentation, there's usually somebody in the audience that says, yeah, well, that's all great, but what does it cost? I can't afford a building like that. So these may not mean an awful lot to you, but the cost of the base building was $180. The fit up was a further $70. So the fit up is the carpet and the ceiling tiles and so on. Total cost of $250 a square foot. That's all in, all design fees and everything. It doesn't include the land. A typical building on campus here, I dare say, is in the 300 to 350 range, and yeah, somewhere around there. So we're at 250. So it's a little bit of an unfair comparison. A university building you would expect it to be a little more expensive. But this is not an outrageous number by any stretch of the imagination. We've tried to figure out, quote unquote, what's the incremental cost. It's in the order, maximum might be 10% on the building. But based on that pricing, we're doing a market rent of $18.40 a square foot. Again, phone the local realtors. That's pretty much the going rate for space around here. So, and we're feeling that we got this building at pretty much no extra cost, minimal at best. So that was kind of the building side of things, and so we were actually feeling pretty good about this, and we said, you know, life goals, you know, create most energy efficient building, check. And so we said, well, if we can do that, why don't we be carbon neutral? That's the buzzword these days. I mean, look we're most of the way there with our building. This should be pretty easy. So we joined Sustainable Waterloo, organization here in town, which is promoting sustainability among businesses. And we pledged to be carbon neutral in 5 years. And they have an interesting rule that I like that says you can't be carbon neutral by buying your way out of sin. Most people say we're carbon neutral, and the way they did that is they just bought a whole bunch of credits from wind farms and so on. So they didn't really change their building or their practices at all. They just bought credits that somebody else did the right thing. Their rule is you can only buy up to 50%. Or another way of saying it, if I save 1 unit of energy, I can buy one. So it's a real nice lever on that. To make a autonomous building that doesn't require any energy. Well, no one's done it. Well, we used to do it. We lived in caves. That was the zero, but yeah, we've progressed past that a little bit. So no one yet has come up with a zero energy building. So it's a pretty hard thing to do. But this at least is feasible. If I can get it down half, then I can at least buy the other half. The catch is, in being carbon neutral, it's not just the energy use of your building, it's everything you do. So it's your materials that you use, the paper for your photocopiers, it's travel, commuting, and all those sorts of things. So we said, sure, that should be easy, no problem, we'll go for that. So we went, and the first thing you have to do is you have to go out and do a carbon inventory. So we did that, and that's kind of where we then became a little more humble in what we've achieved. So good news, our utility use, we were stellar. That's this, I lost my pen here. That's that purple wedge, the 10%. Of all the carbon associated with our business, only 10% is associated with our building use. Great job, 80% reduction, but it's 80% reduction of probably the smallest wedge. What went wrong? 51% of our carbon footprint was commuting, so that's people driving to and from work. And we were talking about this earlier. If I build a green building and put it out in a farmer's field 20 miles from town and everybody has to drive their car to it, is it really a green building? This would suggest no, that's terrible. So 51% of our carbon footprint was associated with commuting. Shame on us, the other 39% was for business travel. So driving and flying around the country trying to create green buildings is costing us another 39% of our carbon footprint. So although we set this great goal of going to zero, we've dug ourselves a really deep hole to get into. So what have we done? I'm a great believer in you manage what you measure. So all of a sudden now our focus has turned to transportation energy. We got to get our transportation energy down. So what have we done? We have a online tracking tool that our employees use. The same way when you go in every day and you fill your timesheet, I worked so many hours on this project, so many on that. The same thing you do is you said, how did I get to work today? Did I drive? Did I carpool? What kind of vehicle did I drive? And so it's just like your timesheet. You fill this all in, and just like a project where we track how many hours you spend on a project to make sure we're making a profit on it, we also track how many kilometers people are driving and what our carbon footprint is. And we can then see who the offenders are, and there's a mechanism to get people to encourage them to use different forms of transportation. So how are we doing? So here's our 2009 results. So again, 2008 was our initial one. Here's where we are in 2009. We've got a 28% reduction in that. And you can see again, the big chunk there was this lowest bar, which was the commuting. So we've done a number of things. So one is this transportation tracker. So people are doing it. We've also introduced a hybrid incentive that we give up to $3,000 per employee to buy a hybrid vehicle so that they can use that instead of their Escalade or whatever to get to work. And in addition to that, there's a further 11% reduction. We purchase green power for all of our facilities. So our sort of next steps, our ultimate challenge or solution is these two fellows here made use of the Grand River and actually commuted to work by canoe. So that's, if you locate on the river, you can do that. So we now have a car share. So we have Grand River car share is now on site. We've purchased a company vehicle, which is a hybrid vehicle, so that even though you drive your Escalade to work, shame on you, at least if you're going to go out to a meeting in Toronto, you can take the company hybrid car. And so we're continuing to work on that to get our goal of 50% reduction. Some of our ongoing operations, all our paper 100% recycled, organic coffee, green cleaning, all that good stuff. And then this is the green incentive program that we've instituted for the employees. So all employees are eligible for this. So this is the up to $3,000 for a hybrid vehicle. We pay people for, if you want a bus pass or transit pass, we'll pay the cost for that. We give out free rain barrels and composting bins. We have organic lunch program. We have bicycles. We have company bicycles on site. If people want to bicycle to a meeting, they're all available there. So let me just wrap up here with sort of conclusions from this little journey that we've been on. So number one, sort of, you can take it as a good news or a bad news. Huge reductions are available in energy and water. And I hear it all the time, politicians talking on TV about, oh, that Kyoto, really hard number to meet. I don't know if we can get 6% reduction. That's going to be tough. So we get 80 kind of, and did it at essentially no incremental cost. So I don't buy any of that. Big one, and this is the battle we fight all the time, is people are looking for silver bullets. What's the technology that's going to save us? We don't need any technologies. The technologies are all here. It's essentially good engineering design. And that's why I'm glad you're all here, because you got to do it. So stuff, an occupancy sensor controlling the ventilation system. The ERV exists, the occupancy sensor, you just got to wire them together. Pretty straightforward. Monitoring energy use. You can't just put all the stuff in, walk away and say, great, this will be a great performing building. It's an ongoing process of monitoring how you're doing. As soon as you go offside, find out why that is and correct it. And frankly, and then our bigger challenge, buildings are a piece of cake. Now try working on transportation. I'm afraid we all love our cars, and it's hard to get us out of our cars. And that's really the big challenge, and that's what we're starting to work on. As a company, the next thing we're starting to look at is the whole concept of green communities. You can have a whole city of sustainable buildings, but if the city itself is not sustainable and green, you're not going to make the progress. We've got the way we plan cities is typically you have zoning, which says residential goes here, commercial goes there, retail goes there. The only solution is to have highways that connect them all. And so we couldn't design more energy inefficient cities than we're doing now. And I think that's going to be the big challenge moving forward if we're going to try to address our issues of climate change and so on. And finally, I think going green takes commitment from the top. That's the role I provide in our company. It would be the same in this institution or everywhere. It's got to be a top priority, and it is with us. So with that, thank you for your attention.